Hey, in this presentation we are going to talk about use of memory in text processing. Before that, let me introduce myself. I'm Sai Krishna, currently pursuing my data science bachelor's degree at IARE. So what are the objectives of today's presentation? First, we will introduce ourselves with the topic, then the ambiguity that is lying uh, while processing the text, then the basic understanding technique that we use to understand the text information so that machine will be able to comprehend it. Next, using memory effectively during text processing. So let's not waste any more time and begin with the introduction. The performance of a natural language processing system should improve as it reads more and more text. This is true both for systems intended as cognitive models and for practical text processing systems. Permanent long-term memory should be useful during all stages of text understanding. For example, if while reading a patent abstract about a new disk drive, the system can retrieve information about similar objects from memory, processing should be simplified. However, most natural language programs do not exhibit such a learning behavior. We describe in this article how researcher, a program that reads, remembers, and generalizes from patent abstracts, make use of its automatically generated memory to assist in low-level text processing, primarily involving disambiguation that could be accomplished no other way. Virtually all current natural language processing systems suffer from the same flaw: reading text does not make them smarter. They are not able to process text better over time, including texts that are similar to those previously read. This is clearly a problem for systems intended as cognitive models, since human language performance improves in a domain as knowledge acquired. It is also troublesome for practical systems since the lack of learning ability requires all the information needed for understanding to be hand-coded by the implementer. In this article, we describe a computer system researcher whose language understanding ability improves as it reads, primarily by using a dynamic memory of examples to resolve ambiguities that would otherwise require ad hoc disambiguation rules. Researcher reads patent abstracts and automatically builds up a generalization-based long-term memory from them. Example 1 shows a patent abstract P58, typically of those read by researcher. We are concerned primarily with abstracts that describe the physical structure of objects. An electromagnet linear actuator for positioning a transducer over locations on a rotating magnetic recording disk comprising an actuator housing used as a stationary base for supporting various parts, a coil and cart assembly including a clutch, blah blah blah. This is the abstract that we are going to use with the research. So how it is done? First, patent abstracts will be sent into the researcher, then text processing is done, patent abstract representations are made, memory update and generalization is done. Generalization-based memory will happen continuously until an external flag has been raised. Next, intelligent question answering will enable the researcher to learn as it reads more and more text. It should be emphasized at the outset that a researcher is an experimental system. We use it as a testbed to study issues in generalizing complex object descriptions, intelligent questions answering, as well as the natural language processing issues discussed in this article. As an experimental system, we do not expect researcher to be able to handle every example we give it perfectly from the beginning to end. Although robust understanding the ability of a system to understand text, it is not specially prepared for is our ultimate goal. We believe that the development of researcher today indicates that the methods we are using have great potential for the development of intelligent information systems. Despite its experimental nature, Researcher is a substantial computer system that has a dictionary of with over 1,300 word definitions. It runs on a DEC system 2060 and processes each patent abstract in a few seconds. Almost all simple examples can be processed accurately, although Researcher is not at a stage where the quantitative evaluation of its abilities is useful. The system has been tested on over 130 real patent abstracts. While not all of these are processed perfectly, many are handled quite well. particularly considering the complex nature of the text. Close analysis of examples indicates that with the proper information in memory, most of the abstracts could be processed quite successfully. So, the ambiguity that lies with these? Human text processing proceeds at many levels simultaneously. Such processing presumably includes the access of detailed long-term memory for the purpose of finding information relevant to a new text. Information from memory should be useful in assisting low-level processing, but exactly how to use such information is a difficult problem. Earlier work on the use of memory in text processing has suggested that the memory access might help in reallocating resources, how and when to apply computational effort, and identifying the important parts of a text. However, there are imprecise ideas and are difficult to apply. For example, IPP, an earlier program by the author that read, remembered, and generalized from news stories about international terrorism, would know from accessing memory that the destination of a hijacking in a story that began a United 727 and en route to Miami was likely to be Havana. However, it was not clear how to use this information if the story simply continued to Havana. It is quite easy to process this text without the expectation, and memory just provided a redundant cross-check. Providing default information was IPP's main use of memory. Had no destination been mentioned in a Miami-bound hijacking, IPP would have been for Havana, while IPP did in this manner get somewhat smarter as it read. Its improvement was not as great as one would have hoped. It is our feeling that the best way to use detailed memory information during the text understanding in the context of current system is to identify specific tasks where memory can be applied. We will present here a set of questions that arise during text processing that can be most easily answered and often can only be answered by accessing long-term memory. These questions are particularly important in the ambiguity resolution necessary to achieve the kind of robust performance that is crucial for researchers' learning tasks. We are proposing using memory for understanding as opposed to general semantic information about words or concepts. By memory mean an appropriately organized knowledge base of detailed information acquired from previously read text. This can involve specific examples and/or information generalized from examples. While general semantic information is crucial for our conceptually based understanding methods, in order to resolve many understanding questions, it will be necessary to look at the very detailed information in memory in our case, how the objects described in patterned abstracts are constructed, and how they relate to each other. To illustrate why memory is needed, consider the following simple example 2 and 3. In example 2, there is no way to determine whether XXX is the material used for the read or write head or for the disk without knowing something about the objects involved. Different XXX would be analyzed differently. In some cases, a single XXX could lead to different analysis depending on the state of memory. For example, if XXX was plastic, our analysis would depend on what we knew about plastic disks and plastic read-write heads. Well, let's talk about example 3. The resolution of ambiguities such as those in example 2 and example 3 is an area where we will believe memory can be immediately useful in text understanding systems. While the specific methods described here are for researchers and so are tailored to read patent abstracts, ambiguity is a problem for all natural language tasks, and we feel our memory-based resolution techniques will be widely available. The problems of disambiguation is not a new one. Linguists have looked at problems of ambiguity for many years. One linguistic method to resolve certain ambiguities is the use of semantic constraints. To take an example adapted from, suppose we are trying to analyze red car sale and determine whether red modify car or sale. If our definition of red says that it only modifies physical objects, then we can determine the correct modification, assuming car is defined as a physical object and sale is not. The application of semantic information, including semantic features of words, to resolve ambiguity has also been widely used in artificial intelligence research. Constructions similar to those we will look at have been considered in. While the use of semantic characteristics is a useful technique indeed in many situations, it is only possible approach. It has several major problems. The disambiguation information is static and must be predefined for the system, so cannot react to changes in the domain. The semantic categories that are defined are often ad hoc. For example, if we are analyzing leather car seat, only a very specialized set of properties would serve to be disambiguated. On the other hand, looking in the memory built from a specific example for information about leather cars or leather seats should prove effective, as we will show, since we would have examples of leather seats but not leather cars. Let's talk about the basic understanding techniques. Researchers processes patent abstracts by using basic syntactic rules to identify objects in the ultimate representation, and combining these objects by adding appropriate relations to their representation. The goal of the text interpretation phase is to build up descriptions of objects, including physical and functional relations between various subparts of the objects using a canonical frame-based representation scheme. If we look back at the abstract shown earlier, P58, we can see that different syntactic structures can function quite similarly. For example, the phrase functions an electromagnetic linear actuator for positioning a transducer, and a hypothetical alternate phrasing, an electromagnetic linear actuator that positions a transducer, are functionally equivalent but involve different syntactic structures. Since subtle differences in syntactic structures do not seem to be crucial for device patent abstracts, this domain provides an excellent source of text for testing semantic-based understanding methods that build conceptual representations directly from the text. Researchers use only very basic syntactic information. Most of the difficult disambiguation problems are fundamentally semantic. The advantages of minimizing the use of syntactic information for cognitive models were discussed in detail. Now, using memory during text processing, how it is being used. So in this section, we show specifically how a long-term memory built up from text can be used to resolve the ambiguity questions specified in section 2.2. In the context of researcher text understanding process, all of these questions involve determining which of several possible physical structures is most plausible in order to perform disambiguation. Integrating memory access with text processing. Asking the disambiguation questions presented in section 2.2 fits in nicely with the overall researcher text processing algorithm. Researchers save and skip non-group strategy naturally accommodates memory-based disambiguation. As the program is processing the items from its short-term memory stack, it keeps tracks of the identified mementos that can be modified. The mementos described by the head noun, the most recent noun and certain intermediate nouns. As researchers continues to work back through the stack, if there is more than one distinct object described in the noun group, memory can be queried to determine which objects new word modify can relate to. Without using memory, it is necessary to employ a set of complex and rather unsatisfying heuristics to determine how the parts of noun group fit together. Before there is anything in memory, this is what researchers does. As memory grows, we can achieve much better results by using dynamic knowledge base for new domains. People probably initially apply information from other domains, but we do not do this with researcher. Memory access fits equally in the MEMET, the relation phase of researcher's text processing algorithm. Researcher maintains short-term memory buffer with the objects that can be targets of a new relation, usually those specified by the head noun of a sound noun phrase and the most recent noun, although there are other possibilities. Let's take an example of the motor spindle. Now, the key processing in InfoGo takes place at the end where the spindle is read. As researcher works backward through the words it has saved and skipped, it must determine the relation between the concepts of drive shaft and spindle. It searches memory for a relation between those concepts, finding that it can only postulate an unknown functional relation between the objects. So this is the how we are doing that. So if the general disk has a read or write head on top of its disk, while a specialized version had it underneath, we would use the on top of relation resolving the disk drive head. Several other problems arise when looking for relevant examples for use in text understanding. We will mention two here. First, our scheme would require the refinement to handle certain elements of context in a very broad domain. For example, suppose research in memory had descriptions of stereotype tables as well as describes. The relation between objects such as motors and drive shafts might be very different for the two devices. Next, problems with memory access. So, setting up the memory. What happens if more than one relevant instance is found in memory? Obviously, this will occur frequently when memory is complex at the moment. We have one heuristic for use in this case. While multiple relevant examples are found in memory, those nearest the top of the generalization hierarchy, that is, in the most general object descriptions are used. So if used in the most general object descriptions are used if the general describe has a rate or height. Okay, the same is true in considering examples where one of the ambiguous cases is so obvious that Bayesian consideration indicates that it would not likely to occur in text, in which case we would need other heuristics. This figure is a machine implementation of what I just read. So what's the conclusion? Memory application is an absolutely necessary if we wish for our understanding systems to take advantage of all the information they possess to improve performance. However, we must delineate exactly how memory should be used. In the researcher framework, simple syntactic rules driven by generic memory structures limit the possible ways that a representation can be constructed, and searching detailed memory resolves ambiguities. Thank you for listening. Thank you for listening.